Let's start the second session of this conference, the workshop, online workshop today. My name is Tomohiro Sasamoto from Tokyo Institute of Technology, and I will chair this session. And we have two speakers, and the first one is Sriram Ganeshan, and he's going to talk about Hamiltonian structure of 2D fluid dynamics with broken parity. Okay, so please.
Yeah, thanks, Tomohiro. Thanks a lot for inviting me for this workshop. I hope to catch up some of the early morning ones over YouTube at some later time. So thanks again for the organizers for inviting me for this workshop. So today I'm going to speak about, I'm from City College of New York. It's in New York City. And so today I'm going to speak about Hamiltonian structure of 2D fluid dynamics with broken parity. Okay, so this talk is based on this archive reference that is already posted. And the bulk of the heavy lifting in this project is done by the postdoc in our group, Gustavo Monteiro. And this work is also in collaboration with Sasha Abanov from Stony Brook and Simon Center of Geometry and Physics. Okay. So the motivation of this talk is based on systems that have been catching a lot of, attracting a lot of attention in recent years. So these are classical fluids with broken parity in 2 dimensions. So you can, such systems are kind of ubiquitous in nature. Parity breaking is kind of seen in almost several aspects of our everyday life, and it's also kind of very relevant in more abstract systems like quantum Hall effect, and more recently these engineered active chiral fluids, and this, think of classical fluids in magnetic field or in a rotating frame, and also some internally driven active materials such as living matter. So what I mean by parity breaking is that I want to think of a constituent system that composes of this fluid where I have some microscopic dynamics that breaks the parity. Like, for example, think of a spinning top. And so these pictures are the examples of the systems which kind of manifest fluid-like behavior at long wavelength regime, which has this parity breaking effects. And you can think of these fluids as quasi 2-dimensional or 2-dimensional. So we will be, for all this talk, we will be staying in 2-dimensional world. Okay, so the first picture is of a recent experiment in William Irvine's group. So what the system does is that you think of this system as this fundamental motif of the system is this hematoid colloid. And this hematoid colloid has some magnetic moment that is pointing in a particular in-plane direction in 2 dimensions. And then such particles are situated in a tank. And then outside the tank, there is an in-plane magnetic field magnet that rotates and also rotates with these particles with the magnetic moment following this magnet. So when the density of such particles are huge, what happens is that these particles coalesce into some kind of a fluid behavior where each fundamental unit is spinning on its own axis. So these orange dots can be thought of as single particle, actually single fundamental unit. And these orange region is like the droplet that can be formed by such particles. And then at the long wavelength regime, you can think of these droplets as some kind of a fluid dynamical behavior where the individual spinning, chiral spinning at a fundamental motif level is translated then into a net parity breaking effect collectively on the fluid. Okay. And then you can also think of much simpler system where you can think of spinning tops that are spinning in one direction. And then you can think of these tops confined into some space, and then these are colliding with each other. And you can think of the coarse grained such systems, and in some long wavelength limit, these also kind of in a zoomed out version behave as a collective dynamics. And these collective dynamics can be modeled by hydrodynamical equations where the parity breaking part of that hydrodynamic equations plays an important role in their phenomenology. And more recently, people have encoded these parity breaking effects in hydrodynamical systems. They kind of postulated that such effects can be realized in living matter also, like swimming bacteria, actomycin networks, And even going beyond 2 dimensions in 3D also, such effects have been realized. I will give you a reference for a paper by Lubensky and Markovich, where they claim that such parity breaking hydrodynamical coefficients can manifest in active biological living systems as well. And since I'm more closer to condensed matter community, it's my obligation to highlight a particular system where it's graphene electron fluids, where it's some specific regime where your electron scattering length is the shortest scale. And when electron length is the shortest scale and the much smaller than the impurity scattering scale and the size of the sample, then these electronic systems kind of create a locally conserved momentum region and behave as if they are a puddle of fluid. And these puddle of fluid, the transport of such fluid-like behavior of graphene electrons is very different from the ohmic region. So these are kind of fundamental behavior of the fundamental motif of what is being known as viscous electron fluids. Okay, and at a macroscopic scale also, you can see this is a picture of a Jupiter atmosphere. And these are these chiral vortices that are formed due to the spin of the Jupiter. And so you can think of the Jupiter atmosphere as a collection of vortices that have some chirality, same chirality associated to it. And in some coarse grained limit, these chiral vortices can lead to a fluid-like behavior that manifests many of these 2-dimensional parity breaking effects. And such chiral vortex fluids were discussed by Abanov and Wiegmann some years back. So these are the typical systems that I have in mind when I talk about my hydrodynamical framework. So, but what I'm going to talk about, so the active area of research in this related to these systems can be divided into 2 parts. Like one is to construct the library of broken parity phenomena in these 2-dimensional fluids. Like, for example, solve a typical hydrodynamical fluid dynamical problem. Think of how if you drop a ball in such a fluid, such a medium, what is the lift force on that ball? You can ask, if you place a bubble in such a fluid, what is the equilibrium shape of the bubble? What is the free surface dynamics or surface gravity waves, structure of the surface gravity waves, and so on and so forth. So these are the electromechanical responses that experimentalist or a theorist would be interested in asking questions about such systems. So there's a huge library of broken parity phenomena that has been actively studied in last few years, and some of my work has been focused on that. And this is a list of all the, not complete list, but some list of all the properties that people have studied in the system that they hope to see as a response in these broken parity fluid-like systems. But this is not the focus of this talk. This talk is going to be focused on more formal aspects of such hydrodynamical systems. So the type of questions that I will be asking and will be addressing in this talk is that, let's say if I write a hydrodynamical theory of broken parity systems in general, by coarse graining some broken parity system, I land at some hydrodynamical equations of motion. So then I am going to ask this question, what is the structure or what are the constraints on this final hydrodynamical equations if my starting point is a microscopic Hamiltonian system? So you can start from any microscopic system, molecules bouncing off each other in a container, and it can be anything. And I'm going to coarse grain, I can think of coarse graining such a system, and I arrive at some hydrodynamical equations of motion. So the question, I'm going to ask this question in reverse, where I say that take any broken parity hydrodynamical system, and then I'm going to ask what are the constraints on such equations or transport coefficients under which they can be systematically derived from some Hamiltonian system. In other words, I'm going to ask this question in 2 parts. First, since there is an intuition that these parity odd coefficients, which I will explain in a couple of slides, are non-dissipative in nature. They don't do any work on the system under some responses. So the question is that, are these non-dissipative coefficients automatically result in energy conserving hydrodynamical equations of motion? And if yes, then how many of these are there any constraints, or how many of these energy conserving hydrodynamical systems possess Hamiltonian structure? Okay, and the reason I want to study this is that you can kind of classify these hydrodynamic parity broken systems from the point of view that how many of them require some activity, like how many of them can be deduced from which class of these hydrodynamic equation necessarily require some activity at a local level, or which class of hydrodynamic system can be purely derived from an equilibrium setting, and so on and so forth, and which one of them have a Hamiltonian structure of fluid dynamics. So this will be the focus of this talk. So before diving into the setup, let me review the hydrodynamical equations that I will be focusing on. So before introducing parity breaking, let's consider first order hydrodynamics that with isotropy and parity symmetry. And I will be focusing on adiabatic flows for the rest of my talk. But this is just a review of the kind of equations that I will be restricting my hydrodynamics to. So the first equation is continuity equation, which is, in other words, it's a mass conservation. And this is the continuity equation for such system. And then the next equation is the momentum conservation. So these are the only two conservation laws that are long lived in my system. And I'm going to assume that all the temperature effects and everything are equilibrated at much shorter scales. And the Tij is the stress tensor of my system, which encodes, which contains up to first spatial gradient terms of the derivatives of this velocity. So this is where I truncate my constitutive equations, where I express Tij in terms of velocity and in terms of this fluid velocity. And you notice that the only terms that are allowed are all possible first gradient effects. And under such circumstances with isotropy and parity preserving system, in general, you can have three well-known transport coefficients, namely shear viscosity, bulk viscosity, and this another one is called internal torque, gamma. And notice that with parity preserving structure, all first order terms are dissipative in nature. So for the rest of this talk, I'm going to set all these coefficients to 0 straight away. So I'm not going to focus on any dissipative coefficients at all in this talk. Okay. Okay. So now let's move on to fluid first order hydrodynamics in 2 dimensions with isotropy and broken parity. So the continuity equations remains the same, and the momentum conservation equation acquires this 3 additional coefficients in the form of this Hall stress tensor or odd stresses. And notice that in the previous case, I have already set all the dissipative coefficients to 0. So that's why they are not appearing here. Otherwise, there should be in total 6 coefficients, but 3 of them are set to 0 owing to the fact that they are dissipative in nature. In this Hall stress tensor, there will be additional 3 coefficients. All these coefficients preserve isotropy, but they are parity odd in nature. And this can be seen by the fact that there is always some epsilon tensor lurking around in the star. Notice that the star notation, which you are going to see again and again in this talk, it just means that if a star of a vector is just a 90-degree rotated vector, and the notation is that this is a Levi-Civita tensor contracted with the vector epsilon ij aj. So another way to say that is if I have a vector ax star, this is equal to ay, and ay star is equal to minus of ax. Okay, so this is the notation that I'm going to use frequently in this talk, that star of a vector means just this definition in 2 dimensions. Okay, and so there will be 3 coefficients here. First is the well-known Hall viscosity, which has appeared in various contexts ranging from quantum Hall effect all the way to active matter systems that I was defining earlier in my first slide. And the second one is odd pressure. Means there were no names to this coefficient, so we are kind of coining these terms. But if you have any well-known terminology for these coefficients, I would be happy to learn. So there is second term is odd pressure. And the reason it's called odd pressure is because note that it comes with delta Ij term. So this can be kind of absorbed into this pressure term, and you can think of it as a vorticity shift to the pressure term. That's why we kind of call it odd pressure. And the third one is called odd torque. And this odd torque meaning that is associated to this divergence of V. And I will explain in next slide what do having these coefficients is, what are the implications of having these coefficients for fluid responses. And note that these are all first order responses, and I'm going to stick to the first order responses. Okay. Any questions so far? Please feel free to ask any questions during the talk. We have enough time. Okay. If there are none, let me proceed.
Sriram, so
yeah.
So these are all extra. These are all transport coefficients. Right? They lead to dissipation. Is that right?
No, these don't really lead to dissipation. Please, I will show you in next slide why they don't lead to dissipation. So the ones in the previous slide, these lead to dissipation.
Okay, but those you dropped, right? Yeah.
Yeah, those I have dropped. So I want to stick to, since I'm asking the question about Hamiltonian structure and everything, so I'm going to drop everything that is dissipative to start with, which are obviously dissipative.
Sriram, these terms are time irreversible, right? If you do it.
The dissipative ones are parity even or time reversal preserving.
If I change t to minus t, they don't change sign.
No, they don't change sign. Means this particular, I think that can be seen.
Momentum conservation equation. If I change t to minus t, they do change.
These are just Newton's laws, right? So so actually the better way to. Oh, okay. Okay, this is a good point. So so there are two senses in which one can think of time reversal. One is through this equilibrium notion of micro reversibility. So it's kind of time reversal in the sense as in that because there is a dissipation in the system, if you reverse back, there will be some dissipation in the system. But that time reversal breaking used in an equilibrium notion is not what I meant by when I say parity odd. So the better way to think about is not in terms of time reversal, but parity symmetry in 2 dimensions. So the parity symmetry is like the symmetry under which you switch one of the coordinates and then see what happens. So switch y to minus y or x to minus x, and then see if this preserves the symmetry. So what I'm going to say is that all these dissipative coefficients are parity preserving. So parity is the right way to think about it. The time reversal has to.
They are presenting dissipation in the system, right?
Yes. So there is a dissipation at the microscopic scales because see, if you have a bucket of water, it has viscosity. So the question is that the viscosity, where does the dissipation go? It goes into this microscopic scales in the system. So the time reversal is not the kind. It has two notions in dissipation. If you think about dissipation, that system has a dissipation. In that sense, there is no time reversal in a micro reversibility sense, in an equilibrium sense. But the time reversal I will be breaking is by applying magnetic field in the system. Let's say if you have applied a magnetic field in a 2-dimensional system, then there will be a explicit breaking of time reversal symmetry. This is a subtle point, and I would like to distinguish between them. So to avoid this confusion between micro reversibility and explicit time reversal breaking, the better symmetry to think about is parity symmetry. So that's why I'm kind of focusing on parity symmetry. And the way to track parity symmetry in these first order responses is that if you have this stress strain relationship, Tij is eta ij KL, dkVL. So this is like a stress tensor to the strain rate relationship through this rank 4 viscosity tensor. So parity odd and parity even can be tracked by the structure of this tensor. If you switch the pair of these indices, KL, IJ, so if you have a negative sign, you have parity odd, parity symmetry broken in the system. And if you have a plus sign, it's parity preserving. So all these coefficients that I'm talking about arising in this eta IJKL are symmetric under the exchange of these first two and last two pair of indices. But in the coefficients that I will be talking about with the subscript, with the superfix H in it, you will pick up a negative sign with the switch of first two and last two indices, which is an indication that there is a parity odd structure in the symmetry. So for the purposes of this talk, I'm going to separate out the time reversal absence through dissipation and the explicit breaking of time reversal symmetry by applying a magnetic field by talking about parity symmetry instead.
Can I ask another question related?
Yes.
Well, just to clarify, so what you mean is that with the explicit time reversal breaking, but without the dissipation term, you wouldn't have increase of entropy of the local fluid cell, essentially. That's what you would mean?
Yeah, exactly. Okay. So this is on top of it, I'm only going to consider adiabatic flows. Actually, this is a subject of this, that how are, so I'm going to frame it as a question, what you have asked for the rest of this talk, that if you have these non-dissipative like coefficients, does it mean that your hydrodynamics will automatically be energy conserving or not? So that's the question of this talk. So I will address it systematically.
Okay, so in general, there is a general way of writing the entropy of the local fluid cell and all that. So couldn't you just evaluate that from your equation with parity symmetry breaking and see if it increases or see if there is some kind of
yeah, so this is what I'm going to do. But since I will be going to restrict to adiabatic flows, instead of entropy, I'm going to talk about the dual variable energy density. So yeah, I'm going to say if the energy density is a conservation law of the system or not. I'm going to ask this question.
Yeah, okay, thank you.
Yeah, so energy is the opposite sign for if you want to track through entropy. So I will be tracking energy density. Yeah. Is any other questions? These are all good questions actually, and it is relevant to my talk. So please feel free to ask if some of my answers are not clear. Okay, so let me proceed. So these are the three transport coefficients, and let me give you some physical intuition of what these what does the presence of these coefficients do to my system. So as I said, there are three responses: the Hall, viscosity, odd pressure, and odd torque. So let's say if you try focus on this figure, if you try to shear your fluid, let's say these are the walls of some. I place the fluid between these two walls, and I try to generate a shear flow. And if I do a shearing flow, the dissipative coefficients would have acted opposite to the motion of my shear. So these are the dissipative coefficients. Means I've set them to 0, but just to contrast them with the dissipative case. So if I try to shear the flow, then all the dissipative coefficients will oppose the motion. They will act opposite to the direction of my motion if you calculate the forces. On the other hand, both odd viscosity and odd pressure term apply forces perpendicular to the applied shear. So then in that sense, there is no work done. And this normal direction comes from these presence of this epsilon tensors in all the transport coefficients. So hence, since there is no work associated with this shearing motion, because all the responses to my fluid deformations are perpendicular to the deformations itself, So there is an intuition that the at least first two coefficients are non-dissipative in nature. And also the third one, which is called odd torque. So if you create a sink or a source inside your fluid, then, or let's say if there is a flow that is acting outward because of a sink, source that is placed at the center of the fluid, then you will see that there will be a force due to odd torque that acts tangentially at the surface, or again normal to this outward going flow. So all these three odd responses in first order hydro are non-dissipative in nature, taken individually just by intuition, because they act perpendicular to the applied deformation. So then that kind of sets up the goal of this talk. Despite individually their responses are non-dissipative in nature, are these naturally energy conserving? So let's say if I start with a hydrodynamic equation of motion, which are naturally energy conserving, naturally non-dissipative with only these transport coefficients, are they energy conserving by definition? And if they are energy conserving, then are they? Sorry.
Sorry, Sriram, maybe I have a question. Maybe it's similar to what you're saying. So, you know the Poisson brackets here, right? So, can we frame the question as if, do we know a term in the Hamiltonian that produces these terms that are on a slide?
Okay, so you are at almost the last slide of my talk. So, Manas, I think the first step, as I will explain, is that you have to find if there is a conserved energy density, which will be the Hamiltonian of your system, right? The integrated energy density will be the Hamiltonian of the system. And to generate the equation of motion, which I already know because that's my starting point, I need to construct some brackets. Okay, there will be some subtleties in the brackets, and I will come to it in like the second to last slide of my talk.
Okay, thanks. Thanks.
Okay, so the first question is, because intuitively these responses are non-dissipative in nature, does the hydro itself has a conserved energy density in the system or not? Okay, so that will be the first question. So before going there, let's see how we study energy conservation for an ideal barotropic fluid. And barotropic fluid means that the density is a function of pressure alone. And as I said, I'm not going to consider any other equations because all of them are relaxed at much shorter time scale. So these are the only long-lived conserved quantities that I'll be focused on: the momentum conservation and the mass conservation. And so here I'm talking about ideal barotropic fluid. So I have set all the first order transport coefficients to 0. So the stress tensor is just given by this negative of pressure delta ij. Okay, so then how do you construct a third conservation law, namely for energy? So the way to do it is that, since I'm talking about adiabatic flows as for ideal barotropic fluid, energy conservation follows from the continuity and momentum conservation. So I don't need to postulate another conservation law. So it just follows from the first two equations here. Okay, so then the technical procedure is to contract Vj both sides of this momentum conservation equation and keep massaging this equation using the continuity equation till you get a conservation law of this form. Okay, where dt is this so-called energy density, which is scalar. So just contract the momentum conservation equation with Vj here, and then just keep rewriting these equations using the continuity equations till you can express it in the form of dt of some scalar quantity. Since notice that I'm contracting with Vj, it will generate these scalar terms. And then for some current Qi, energy current, associated energy current Qi. And it turns out that the conserved energy density is what you would have expected here. It's this conserved energy density is half rho V I square plus the internal energy density, which is only a function of rho. Okay, and this internal energy density is related to this pressure via this relation, and this is just the equation of state for this ideal barotropic fluid. Okay, so this is the strategy to check, in some sense check. It's obvious because it's an ideal fluid, there are no stresses, but this is the procedure that I'm going to run even in the modified case where I include this first order Hall coefficients. Okay, so the energy is conserved. So what about Hamiltonian structure for the same? It's a warm-up example, so I'm just setting it up, and I will identically follow the same procedure for the more general case as well. So the Hamiltonian structure for ideal barotropic fluid, what I mean by Hamiltonian structure is that I need to have phase space, the configuration space of my system, and I need to have Poisson brackets, and then I need to have an Hamiltonian. So I know what my Hamiltonian is, because in the previous slide, I just calculated the conserved energy density, and the integrated conserved energy density can be used as a Hamiltonian. Notice that I'm changing slightly the notation to make contact with the canonical form. I'm going to introduce what I call as momentum density. And this momentum density, this script J is given by rho VI. And if you substitute this, it's just half rho VI square. Okay, so this is the Hamiltonian. I know it from my conserved energy density. I also know equations of motion because that's where I started from. So I know the hydro equations of motion. This is just a continuity equation and the momentum conservation equation. Okay, so what I don't know is what brackets I need to choose or I need to construct such that I start from this Hamiltonian and get these equations of motion. In fact, you can construct these brackets, and it turns out that these are the Poisson brackets that you need. This is just the rho commutes at all points, and these are the rho j brackets. And the most well-known in mathematical terms is the momentum bracket. So this has a very interesting structure. By itself, it's called diffeomorphism algebra. And this diffeomorphism algebra, which is supplemented by these additional two density Poisson brackets, are called extended diffeomorphism algebra. So if you start from this Hamiltonian and run these brackets on Hamilton-Jacobi equations, then you will get the right equations of motion. So this was first done by Zielinski and Wolowick in this paper, and they were studying fluids in the context of condensed matter system like superfluid helium and all those things, and when they constructed the Hamiltonian structure of these ideal fluids. Any questions here in this warm-up example? Because I'm just going to crank this machinery for the more general case.
Actually, can I ask questions also?
Yeah.
So yeah. So well, one thing I think if you start with a system of particles and with interaction and just do the standard canonical construction and then kind of fluid averages, you get that type of algebra. So you can actually, I think, deduce it with a fluid approximation from macroscopic.
Yeah. So there is something called Poisson bracket approach. I think it was first developed by P.C. Martin in 70s, where they were trying to study hydrodynamics. It's called Poisson bracket approach, and they were applying it to fluids of all kinds, like fluids of liquid crystals and very weird objects. And so then there is a systematic coarse graining procedure. You start from microscopic Hamiltonian and coarse grain the system, and then coarse grain the brackets as well. And in the center of mass frame, you do get diffeomorphism algebra.
Yeah, that's right. Yeah, so I guess
so diffeomorphism algebra is associated with the center of mass coarse grain structure of this microscopic system as well.
Yeah,
but
now just my question then was that how unique is the structure for generating these equations of motion?
Actually, I think you need some mathematical theorems that you don't have any central extensions to this algebra. And we believe strongly that there are no extensions, at least in 2 dimensions. So I think this is with reasonable confidence, we think that this could be unique, but I may be wrong. There is a buried mathematical literature where it exists central extension.
Yeah, okay.
So we asked Boris Kessin if there exists. He was not aware of it. So I will defer to him.
And then when you do your parity breaking, can you also do the approach from microscopy? But maybe you just
yes. So there is a recent paper by Lubensky and Markovich where they did exactly the same for parity breaking for both 2D and 3D from there. So I will give you the reference for that paper. In fact, that paper motivated us to ask this question, but there we are kind of running opposite. We are saying that if you start from hydro equations, what are the constraints on the coefficients that can that can be derived from microscopic Hamiltonian? Because they kind of did not consider, so they run the movie forwards and then they get what they get. So, but there is always this lingering feeling that, oh, maybe if you would have changed your model, you would have got another coefficient. But so that's why we kind of did this in the opposite direction, where we asked what are the general constraints on these coefficients that can be deduced from starting from a microscopic Hamiltonian system.
Yeah, thanks a lot.
Okay. Any other questions? Okay, so these are the two warm-up slides basically for energy conservation, and I'm going to exactly apply the same thing for the more general case. Okay, so now, as I said, I'm going to ask the question energy conservation for compressible 2D broken parity fluids, and I have set dissipative terms to 0 because they obviously would not conserve energy. And I want to mention that there are literature in the relativistic high energy community. I think there are papers by, I think going back to Sayanthani Bhattacharya, Kirsten Jensen, and Kaminsky and Moroz, where they asked the same question in the context of entropy current. They were asking this question for the positivity of entropy current and constraining the transport coefficient. And also there is a paper by Loga where I think it's a 200-page paper by him where he studied adiabatic hydrodynamics. And I'm sure that some pages of that will contain the similar discussion. Okay, so here I'm going to consider a baby version of this analysis. So again, I'm going to ask this question. In order to obtain the conserved energy density, I will start from the momentum conservation and mass equation now with this Hall stress tensor. And I want to run the same algorithm to ask this question, can I construct a third conservation law, namely the energy density in this form? Okay, so let me give you the results first. So it turns out that the 2D hydro is energy conserving in two cases. There are two distinct cases, non-overlapping cases. First condition is that in order to construct such a conservation law where your energy density is a third quantity, the first constraint is that this odd torque term plus the odd pressure term should be 0. And eta h of rho can be arbitrary. Okay, and the second case is a bit more involved. Means it's just a linear algebra equation, but it involves an arbitrary function g and an arbitrary constant c. And all these transport coefficients are parameterized via these arbitrary constant and arbitrary function. And if they have such a structure, again, that is the second case under which the energy is conserved. So let me give you this, what I mean by this function g, because I think this will simplify the equations a bit. So I'm going to introduce this notation. So I can rewrite this Hall tensor. So remember that Tij Hall, I can write it as eta Hall ij kl dk vl. Okay, so this eta h Hall can be parameterized in terms of these two terms. The first term is explicitly antisymmetric part. What I mean by antisymmetric part is that this eta bar term is, if you switch ij and kl indices, you pick up a negative sign. And the second term is parameterized by this function g, and then this is this rank 4 split up delta ij and epsilon kl. And this is nothing but, rho g prime is nothing but zeta h plus gamma h. I'm parameterizing zeta h plus gamma h as this negative rho g prime. So in terms of this g function, the first case is just that g is 0. If g is 0, zeta h plus gamma h is this. But in the second case, when G is not 0, it has it kind of parameterizes all these three transport coefficients, and they are not, in that sense, they are not independent. So there is an explicit constraint on this constraints on this transport coefficient under which this parity odd hydrodynamical equations have a third conservation law, namely the energy density. Okay, even the energy density, even though, as I said, intuitively they are non-dissipative in nature, but collectively, if you throw them into hydro equations, how they interact with each other in the fluid responses kind of dictate whether they can be derived from a energy conserving system or not. Okay. And the conserved energy density in this case is takes the more general form. This is the first two terms are the same as before for the ideal fluid that I discussed, but there is a G modification to this, higher gradient G function modification to this. And notice that the first case is very simple. The first case is just when the Hall tensor is antisymmetric. So the G is 0 in the first case. And once G is 0, then you will see that the energy density is not modified at all. So the first case, even though you have higher gradient responses, the conserved energy density is identical to the ideal fluid case. But in the second case where the energy is conserved, there you have this G function and you have a higher gradient modifications to the conserved energy density. Any questions on this slide?
Can I ask a question?
Yeah,
just
sure.
Let's confirm. So in these cases, then there is no entropy increase. Is that what's happening?
Yeah, I'm strictly talking about adiabatic flows. Yes, there is no. So this once you have this conservation law, so the entropy is 0 basically.
So you.
I'm just seeking for those cases.
Yeah, you're just looking for that and looking for energy conservation. So,
yes.
So if these are not satisfied, then there is no.
Yeah, there is no energy conservation.
Right.
Yeah, I will. In the next slide, I will give you an example of when these are not satisfied.
Okay.
Okay, and so what about energy non-conserving systems? So it turns out that you can consider a case that explicitly violates the previous constraint. So if you set eta h and zeta h to 0 and gamma h to not 0, if you plug these relations in the previous rules, you will see that these rules are not satisfied. And under such a situation, you have this Tij, which is just contains this odd torque term. Okay, and then you can see the conservation law has a right-hand side, non-zero right-hand side. And this non-zero right-hand side can be positive or negative depending on the flow and the density configuration. Okay, and since it's not strictly dissipative or it conserves energy, you can intuitively say that such type of systems with this configuration of transport coefficients can only be realized in active matter, which involves local driving. So this already kind of tells you that you can classify systems whether they can come from an active matter or a purely dissipative system or an energy conserving system by this analysis. Okay. Okay. So now let's move on to the Hamiltonian question. So again, as in the ideal barotropic fluid, I will take the conserved energy, integrated conserved energy density to be by starting Hamiltonian. And let me give you the results up front, and then we will discuss how we derived this. It turns out that not all energy conserving systems are Hamiltonian. In fact, for an energy conserving system, so I started with this conserved energy density that I derived in the previous case, and I just substituted Ji to be rho Vi. Again, this is just a momentum density. Okay. In fact, there are constraints. It again further splits into two cases. And these two cases are coming from the previous two cases, but there is an additional condition that is imposed by the conditions for a system to be Hamiltonian. And if you overlap two conditions, you will get two cases under which the conserved energy density would be Hamiltonian. And it turns out that the conserved energy density for case 1 of conserved energy density, which is the G equal to 0 case, you have this particular condition. gamma h equal to negative of zeta h equal to eta h minus rho eta h prime. This rho meaning that I'm taking a derivative with respect to rho here. And eta h is arbitrary. This is the condition for that first case of energy conserving case to be Hamiltonian. And then the second case, it's even more restrictive. The only case, the second energy conserving situation is a Hamiltonian is when gamma h equal to zeta h equal to 0. And then you only have this odd pressure term parameterized by this function g. So you can kind of rewrite this g in terms of zeta and then express the Hamiltonian in terms of transport coefficients as well. And this g function is arbitrary, and hence zeta h odd pressure is arbitrary. So the second case where you have higher gradient terms, corrections above ideal fluid, the only term that can appear in a Hamiltonian system is this odd pressure term through this function g. Okay. So I have kind of said something very, I will elaborate on something that I have said casually, that there are some energy conserving systems that are not Hamiltonian. There is a physics to it. I will explain it towards the end of my talk. Any questions here? Okay. I will explain how this is derived. Yeah,
I have a question. So here in the second condition, so you have assumed that the C is 0, right? So it means the eta h was Z.
Yes, C is 0. See, that's yeah, I have already included C is 0 there.
Oh,
yeah, so C will be 0. And this term will not be here. And the only term that will be here is this.
Okay, but what if this G is a constant of rho? Means, is it necessary that G has to be...
See, G is an arbitrary function. You can set it to constant as well. And in that case, zeta h will be 0 because G is taken. If G is constant, G of rho will be 0. So you will go back to the previous case then.
Okay.
Right. So this will be almost like a G equal to 0 case. If it's set G to be constant, then up to the shift of derivatives, it's still the same case.
Means then the first and second condition are equivalent, right? Just to...
Sort of up to some full derivatives. Maybe they will be important if you have boundaries in the system, where if you do integration by parts, the boundaries are important. So it's only true up to integration by parts. Okay. And integration by parts are important if you have boundaries in the fluid. So they will be important under certain circumstances, but not for the bulk situation that I'm considering here.
Okay, thanks.
Okay, so let's go through this derivation quickly. So again, I start with a Hamiltonian as my integrated energy conserved density. And now I have to modify so the row brackets remain the same. Okay. So I have to kind of construct brackets that give me the equations of motion that I started with. I know my equations of motion. I want to get it starting from this integrated and conserved density. Okay. And it turns out that the only brackets that acquire a modification are this diffeomorphism one, which is this JJ, the momentum bracket. So this is the usual one. And then there is a modification which is taken because of this eta prime, the higher gradient effects. And so for a bracket to be a valid bracket, valid Hamiltonian structure, they need to satisfy two conditions. One condition is that the bracket should be antisymmetric. Okay, so AB Poisson bracket should be negative of BA Poisson bracket. And you can immediately see that that is the case because you have to use this eta IJKL as antisymmetric bracket. And then you will immediately see that it's the brackets, this modified brackets will preserve the antisymmetry. And then using that antisymmetry property, you can also see that the energy is still conserved because of the bracket structure, because this is trivially true. Okay. Typically, you are done. Everything is Hamiltonian, except the fact that your brackets needs to satisfy Jacobi identity as well. Okay. And this is where the constraint comes from. So if you check for the Jacobi identity of the modified bracket, it turns out that they do not satisfy Jacobi identity in general. And they do satisfy Jacobi identity only when they satisfy this condition. Gamma h is eta h prime minus rho eta h prime. Okay, and this condition superposed with the energy conservation condition gives you the net conditions for the Hamiltonian structure. Okay. And a corollary to this finding is that, in fact, this condition, when this condition holds, when you have Jacobi identity satisfied, you can always make a variable change in momentum density such that you can always go back to a J, which is a generator of the diffeomorphism algebra. So JJ is this usual diffeomorphism algebra that you looked at in the ideal barotropic fluid Hamiltonian case. So what I'm saying is that if this condition is satisfied for the Jacobi identity, then what you have is that you can always make such a shift in the variables. This shift is always present, which will take you back to a diffeomorphism generator. And in fact, what I'm saying is that the only cases which are Hamiltonian is where you can find a diffeomorphism generator in some shifted capital J variables. Okay. Any questions here?
Sriram, sorry. So this new term that you added to the Poisson brackets, that is, you are just trying various terms that sort of, along with the Hamiltonian, gives you the right equations of motion, right? That's how you add the new term, right?
Yes. Yeah, exactly. So this shifted term will directly, you can see with some manipulations that, see, my goal is to connect the Hamiltonian to its Hamiltonian Jacobi equations via brackets.
Right.
So
right.
I need to do whatever it takes to do that. And that modification does the job.
Okay. Thanks. And just one question is that, so the usual algebra, so maybe this question was already asked. So there is, one can microscopically start from some microscopic variables and somewhat derive these Poisson brackets, right?
In fact, for the center of mass frame of your microscopic system, you will get this diffeomorphism algebra.
Oh, so you can also get the... No, I'm talking about the new algebra. Is there a way you can derive it from more microscopics? The shifted...
see, if you start from a Hamiltonian system, there is no room for this, right? So you will only get the cases which satisfy Hamiltonian, satisfy the Hamiltonian. So what the two possibilities that you get are either algebra in J or algebra in Ji. And in this Lubensky paper, the script Ji will be it's something they call as, one of them is center of mass and one of them is shifted momentum, actually.
But Sriram,
so you get both of, sorry?
Okay.
Yeah, just to comment on what he is saying, I mean, you can define those variables microscopic in terms of microscopic momentum and position, all this, and use the basic, the Poisson brackets and get those Poisson brackets. So one can get those things from, of course, then it will be between the microscopically defined quantities, but one can get those Poisson brackets in that way and write those equations. Only thing that the Hamiltonian, what you are calling Hamiltonian, we call it free energy functional, which is because the corresponding Fokker-Planck equation gives you the solution as a to the power minus f. It becomes like a free energy than Hamiltonian, but it's the same thing. This Hamiltonian that you have written in terms of density and all that, this has been obtained, by people like Langer and Tursky and those people for studying condensation as continuum.
Yeah, no, absolutely.
So this can be obtained from microscopic, just starting from basic statistical mechanical definition of this microscopic quantities and then writing Poisson brackets.
Yeah, so actually yes, so you can start from, so at least the paper that I was kind of...
And I'm basically talking about, you named Paul Martin, so it is sort of along those lines.
Yes.
One can
Yes, exactly. So the contrast between, not contrast, but what they have done is that they have started from some microscopic Hamiltonian system to begin with, okay? And then they coarse grain their system to get their momentum density, center of mass momentum density and everything. And once you coarse grain it, you arrive at some coarse grained Hamiltonian, which will look very close to what I have written. So this is not nothing new here. And they will also get the brackets which already satisfy already satisfy Jacobi identity and everything. There is no, there won't be any violation to the Hamiltonian structure. You can get, in fact, the algebra that I was mentioning here, they have, in fact, Lubensky followed P.C. Martin's work very recently to apply for this parity odd systems. And they get algebra both in terms of this capital JI and script JI.
Yeah.
They get that. Though what we were trying to do is that if you keep adding more and more coefficients, starting from the equation of motion. So we are interested in cases where it is not Hamiltonian also, right? So there might be cases which are energy conserving but not Hamiltonian, which will be outside their framework because they postulate a starting microscopic Hamiltonian to begin with. So our kind of doing things in the opposite direction allows for us to figure out systems that are slightly outside Hamiltonian and what are the various gradations of these systems outside the Hamiltonian structure. So that's the idea that we take. But
you are doing that in a little bit ad hoc way, isn't it? I mean, you have put some transport terms and then you want to set those terms to 0 and thereby you get conditions. But
no, I'm not setting anything to 0 actually. So let me go back. Actually, this is important. So the conditions, the terms that I've set to 0 are dissipative terms. So the shear viscosity, bulk viscosity, and this rotational viscosity I've set to 0. So if I want to begin asking this question, if what can be a Hamiltonian system, I have to set them to 0 because there is no way you can derive a viscosity equation starting from a Hamiltonian system.
Yeah, right? So you set that to 0 and thereby you get some conditions. And I can see that then you may have some transport coefficients which will look like negative. So it will be more like active systems.
Yeah, exactly. So so I have to. Yeah,
and that's what you are seeing. But how
I have to start from a non-dissipative system a priori, and within that non-dissipative systems, I'm saying that there are certain relationships that needs to be preserved on top of being non-dissipative for them to be actually energy conserving and then subsequently Hamiltonian.
Yeah, and so some of the dissipative terms has to act like active terms.
Yeah, exactly. Yeah, it's if you violate the conditions that I'm saying, just as I was explaining in the one toy example, which does not satisfy the energy conservation, I can see that there is on the right-hand side, it can be both positive and negative. So this particular case. So this condition I'm setting is deliberately choosing which violates the energy conservation requirement. And then I'm saying that what is the structure of this conservation law? It turns out the right-hand side is not purely dissipative, which will happen if you have dissipative viscosity, shear viscosity. It can be both positive or negative. So you have to both pump energy locally and then take out energy locally, which can be done through activity, local activity. Yeah, these are good questions, actually. Okay. Any more questions? I'm liberally going into the discussion time. Okay. So I just want to make one remark that the so-called hydro description of quantum Hall, which you can derive starting from Chern-Simons, Ginzburg, Landau theory, and then rewriting this as a fluid equations, are Hamiltonian because typically people don't see this odd torque term in quantum Hall system. I don't have a very good reason why, but at least the theories don't have these terms. And then they have this eta h, the Hall viscosity, which is a linear function of density in those cases. So as soon as you set gamma to 0, the right-hand side is forced to be, eta h is forced to be a linear function of density. So the quantum Hall situations appearing in this case are kind of automatically Hamiltonian in nature, which you expect because these are realized in the ground state of a quantum system. Okay, so let me summarize the results in this schematic. So I started, so I will go on and consider cases which are energy conserving but not Hamiltonian, and where we have seen them in textbooks. But before that, let me just summarize what we have seen. So the biggest box is the space of isotropic 2D hydrodynamics, and it involves all the coefficients, the shear viscosity, bulk viscosity, rotational viscosity, and 3 of the odd coefficients that I have discussed: the Hall viscosity, odd pressure, and odd torque. Okay, there are 6 coefficients in a first order Galilean invariant system. This is the space of my hydro I started with. And if I want to restrict only to non-dissipative systems, I go to a subset of them by setting the dissipative, obviously dissipative ones to 0. Okay, the reason I'm saying obviously dissipative because the non-dissipative ones are also kind of energy non-conserving in some sense. So that's why I'm using this obviously dissipative as a not obviously dissipative language. Okay, and in these cases, these are parity broken hydro with non-dissipative coefficients. I've set them to 0, and some of them are under the constraint that it is energy density is not conserved. So that's why I kind of put this maybe active matter classes. Okay, and the subset of them breaks into 2 cases. And case 1 is energy conserving non-Hamiltonian system, which is in this bigger box. And these are 2 cases which are energy conserving and non-Hamiltonian. And then further subset within these 2 cases are the cases where these are Hamiltonian systems. So this is the full landscape of hydro theories organized in terms of whether they are energy conserving and or Hamiltonian. Okay. So energy non-conserving systems starting from hydro are kind of not surprising. It's kind of known. It's not obvious conservation law, so it's obviously not known. But what about this shaded region here, where you have energy conservation, but they are not Hamiltonian, owing to the fact that, in fact, they are not Hamiltonian in a very subtle way. They are, you have brackets that generate the equation of motion, but the only point at which they fail is that they do not satisfy Jacobi identity. Okay, so actually there are a lot of mechanical systems of this type, and these mechanical systems are called mechanical system with non-holonomic constraint. So the way to think about it is that within our theory, what we can do is that consider the case 1 where G is 0. So there is no additional G type terms in this Hamiltonian. But I expand my Hamiltonian structure by introducing an additional dynamical variable, which is a dynamical intrinsic angular momentum density. There will be a separate equation of motion of this. So in this enlarged Hamiltonian system, everything is Hamiltonian. They even satisfy Jacobi identity and everything. But I impose an additional constraint where I pin my intrinsic angular momentum density to Hall viscosity, L/2 to Hall viscosity term through this cost function. So in the limit when lambda goes to infinity, I produce correct hydro equations of motion for the cases for case 1. However, the Poisson brackets run into an inconsistency precisely in this limit where I impose this constraint. And you see that this Poisson bracket is inconsistent if I do not satisfy this Jacobi identity case. Okay, so if this is not equal to 0, which I can consider a case, the bracket does not respect the constraint and thereby generate non-Hamiltonian dynamics. So this constraint way of thinking about starting from an enlarged Hamiltonian system and pinning down to something that has non-Hamiltonian dynamics, it has similar flavor in physics of what people call as non-holonomic systems. So notice that I'm talking about some energy conserving hydros that are not Hamiltonian. Okay. In fact, there are classical mechanics have several textbook examples of such cases under the name of non-holonomic constraint. What I mean by non-holonomic constraint is that any constraint that cannot be written as a function of configuration alone. So most of the constraints are imposed as a Lagrange multiplier where you, let's say if you want to constrain a particle moving on a circle, then you will just impose it to be lambda times the equation of a circle equal as a Lagrange multiplier. So those are holonomic constraints. But if you include velocities into these constraints, R1, Rn, and R1 dot, Rn dot equal to 0, then in many cases, they cannot be reduced to non-holonomic, or they also sometimes referred to as non-integrable constraints. So the physics of energy conserving non-Hamiltonian systems can be thought of as a system that is subject to a non-holonomic constraint. And this L pinned to eta h rho is the non-holonomic constraint that violates the Hamiltonian structure via Jacobi identity, even though energy is conserved. In fact, there is a nice textbook example where you can slide down an inclined plane through a knife edge or a skate, where you have to maintain this point of contact on the surface all the time, you have to impose this velocity dependent constraint. Okay. And for non-holonomic systems in general, Hamiltonian equations will have some sort of an almost Poisson bracket, which satisfies the anti-symmetry property and everything, and Leibniz rule, but it does not satisfy the Jacobi identity. In fact, there is a proof that the only cases Jacobi identity can be satisfied are the cases where your constraint is holonomic. Okay, so these are my conclusions, and I will stop here and take questions. Thank you.
Okay, thank you very much for the very nice and inviting talk. Yeah, so there have been already several questions and discussions already, and we have only 1 or 2 minutes for this discussion. So if there are any short questions or comments we would like to accept, are there any such short question or comments? Okay, yes. So, yes, so then, yeah, maybe we stop here and let's thank Sriram again.
Okay, thank you.
But after this session, so we are considering to have a break rooms, right? Sriram, can you stay maybe 20 to 30 minutes after the session?
Yeah, sure. I can.
Okay. Yeah. Then yeah, we will have breakout rooms. So maybe room 1.
Okay, sure.
Yeah, maybe people who still have some questions or comments, you can discuss with Sriram in this breakout room after the session. Okay, so we. Thank you. Yeah.